was the definition of reversible? Great, because we're staying very near to equilibrium, okay? So if a system is undergoing a reversible transition, okay? If something's happening reversibly, it means that I'm staying very near to the equilibrium point at all times. Equilibrium being no change in macroscopic properties with time. Temp seems consistent, pressure, volume, everything's looking consistent, okay? This is not real life, okay? A reversible transition, we can't really achieve it, but if we could, it would represent the maximum amount of work we could possibly do. In reality, a true reversible transition would have to happen infinitely slowly, so you'd move an infinitely small amount, you'd wait for everything to come to equilibrium again, so on and so on. But this is a really good reference point. We can capture sort of, we have an idea of what's the maximum possible work we could do, and then think about sort of how efficient any given process might be if we got half of that out or 30% of that work out. And where does the rest of that work go? If I didn't get my maximum work, where's everything else? If I'm not doing work, what did I do? Some sort of loss. So this might be a heat loss to the surroundings. Some of the other examples we talked about were vibration, friction, noise. Again, something I can't get back, okay? So if we look at this here, what was the name for this, the shape of this curve or this line? An isotherm, right? So this is a very specific case that we talked about, an isothermal expansion case, okay? Pressure volume curves don't have to look anything like this. It can look like a squiggle. It can look like a flat line to begin with. It could be isobaric and the pressure is constant. This is what the curve will look like if we're talking about isothermal ideal gas expansion or compression, depending on which way we go. So the maximum amount of work we could do out of this curve is all the area under the curve, okay? And this is important. One example of an irreversible case is what we showed. And this is this case here. If there was an immediate pressure drop and then the volume expanded, this is how much work we would capture. That's only one way that it could look. It's the only way I plan to ask you to quantify in class. But you should understand conceptually that the real life case could look anywhere under that curve as long as it's less than the maximum amount of work. Yes?
Just to clarify, if it was compression, it would still have this downward curve?
Yes, so if I want to compress, so I'm going to have lessen my volume and increase my pressure. I am still moving on the isotherm, I'm just moving up in this direction now, okay? So the expansion is, of course, I'm going this way to the right. If I wanted to compress, I could go the other way. And either way would be fine. Like I said, this was a very specific case, okay? It doesn't always have to look just like this here. I added one extra note sheet that I didn't write last time. I don't know if anyone looked at the notes from before that I put on Canvas. I wrote this after class. It's just a bunch of words of basically what I just said, but it's me talking about this shape doesn't have to look like this, okay? And so I encourage you to read through it if you haven't already. And then this situation here, okay, so this was our isobaric case. We have constant pressure. So our curve already just looks like a flat line. And I asked last time, true or false, could this be reversible? What was the answer? Yes, I can do this reversibly. Now if I do it irreversibly, what does that look like? I've gone faster, and I'm telling you that I'm not going to capture that maximum amount of work. But in the examples we've looked at so far, taking the area of that rectangle looks identical with the example we have for irreversible and reversible. So it's like, oh no, what do I do with this? What could the curve look like for this irreversible transformation? It could look a lot of ways, okay? I'm not asking you to have a specific quantified way of doing this case, but do recognize that reversible means I'm going really, really slowly between these two transitions, such that if I expand to here, reversible means I could turn around and go all the way back to where I started. Real life cases is once I expand to here, I've lost some stuff to friction and sound and heat and noise and whatever it is, such that I do not have right now enough energy to return back to right where I was. I can't compress it back to where I was. Does that make sense for reversibility? I also got a question last time about reversible with a chemical reaction and this like double-sided arrow going back and forth, and that's not really what we're talking about yet, right? I'm talking about, you know, this ideal gas has expanded. Can I turn around and push it all the way back to where I was before? The answer is, in real life, no, because a lot of that went to entropy, stuff I can't get back, okay? So I just wanted to make that clarification in case anyone thought like it always has to look like these curves. This was just one example, okay? This equation, always true, works every time. Work is equal to negative the integral of PdV if we're talking about pressure, volume, work. This always works. What your curve looks like changes, right? Whether it looks like an isotherm or not. Okay? So reversible represents the maximum amount of work you can do. It's that total area under the curve. Important thing to remind here is this plug-in is only because we're talking about an ideal gas. I can't make this substitution for pressure if I'm not talking about an ideal gas, okay? You need that assumption in play. This substitution also requires that I'm on an isotherm, such that T isn't changing. If T is changing, this equation no longer works for you, okay? And I just want to point that out because if you think, oh, hey, I'll see the words like reversible and I'll just use this work equation every time, it's not going to work, okay? And you'll realize that as you start to fill it out. Sometimes I get answers back on exams where you picked one of the two temperatures and decided to use it. I'm like, that doesn't work. So, you know, you can't read all the cue words in the problem so you know really what's going on, okay? And then again, irreversible represents less than maximum amount of work. Maybe it looks like this shape. It doesn't have to. This is the only example I'll ask you to do in sort of a quantified way. Everything else will be more conceptual. So this is just isothermal ideal gas expansion case, and it doesn't always have to look like that. Just reminder of the summary slide is a nice slide, okay? If you want to remind yourself, okay, what drops out when I have isometric, no work is done, let work be zero. It gives you a nice summary of how to kind of simplify your first law based on any one of these terms.